Thank you, Will. It's been really a pleasure knowing you, sir. Anyways, this is a joint work with a very talented graduate student who's already online, Thomas Pender, and another very talented young mathematician from Japan, Sho Suda, who is also online too, right? Yeah. So let me start with wishing a happy birthday to smiling dot. Thank you. So after the two great talks, I really had no choice but starting with something like this. So this is actually a symmetric 181, 81, 36. 181 is a large matrix, 181 by 181. 81, 1 in each row and each column. As a matter of fact, you can see, on this thick line there, sorry. Yeah, here, this thick line, on the edge, that shows 81, 1. Now, this has a story, of course, you will see that I'm going to link this one to different sort of problems in combinatorics. And before doing that, I want to tell you how you can construct something like this. And of course, this is an old problem. It's been really reconstructed many times. It's not really that I claim, the original constructor of this one. So we start with what I call a Quasi-Balanced symmetric BIBD, order 19. I say balanced because of the 9. So this actually has a twin. So you can just, not on the diagonal, off diagonal, exchange between 1 and 0, you get the twin to this one. And because this is exactly at the middle, I call it Paley-balanced. The matrix, of course, is Paley. So we can permute rows of this matrix in order to make it what I call a standard, namely putting all the ones in the first column, all the ones in the first column, and then 0, and then this is what we call derived part of the design, and this is the usual part of the design. Standard thing, we always do. And then, we talk about an orthogonal array of 10, 9. This is an 81 by 10 array in 9 symbols or 9 alphabets. Let me just show you, part of it. This is the first 10 lines. There are actually, as you can see, there are 10 symbols here, 0 to 8. And what you observe in here that if you pick any 2 rows of this, if you take any 2 rows, let's say row 1 and row 10, row 9, and so on, when you look to the columns, there's only one column which has common elements. The rest are all different. And this makes really the job of making that a part of that symmetric design quite easy. So what we can do now, we can replace these alphabets by the rows of that BIBD, which is the derived part of that matrix. Then what happened really, because there's one element only in each column, the rest are different, so they intersect at a certain number, and there we can count, and it really gives you what I have here. We get here, BIBD 81, 180, 80, 36, 35. This is actually quasi-derived design. So the matrix of order 81 by 180, 81 in each row, and 36 in each column. And of course, when you intersect, when you find the inner product of every 2 rows, you get 35. So this will really constitute the derived part of that original symmetric design. And then I use a weighing matrix. A weighing matrix with these parameters that I've shown in here. The order is 10. 10 row, 10 column. The elements are 0, 1, plus minus 1. Every 2 rows are orthogonal to each other. So what we can do now, we can actually replace all the ones with that previously derived residual part, and minus with the twin of that residual part, and then we're going to get the other part of the design we are looking for. We're going to get a matrix of order 100 by 180, and of course, you're going to get a matrix of 100 rows and 180 columns. In each rows 81, 1, and 41 in each column, and then of course you get the inner product 36, the one that we are looking for. And finally, of course, then we get the design. Okay. So something nice happens actually when you put these two together. With these two parts that we found together, we are going to get the incidence matrix of that symmetric design. So that's what I say. Something nice happens. It really works nice, and indeed, it works not for only this one. It works for many of these designs. Okay. So now we are going to do something. We're going to change every 0 to minus 1. If you do that, we're going to get, actually this is the same matrix, but for your entertainment, I just changed the color, to, yes. Yeah. We're going to get now a plus minus 1 matrix. What is special about this matrix? This matrix has the maximum determinant among all 181 by 181 matrices, and the determinant is the largest if the elements are plus minus 1. This is the largest determinant you get. Either you get the smallest or the largest determinant possible, among all the matrices of this size. So then what we can do, we can actually put 4 of these together, and we're going to get another maximal determinant. Namely, you can see that I actually put 4 of these together, and here. One of them is here, one is in here, another one here, and negative and these are actually identical except, of course, for the sign. We're going to get actually a matrix again with maximal determinant, and the order of this matrix is 362. However, this is not the only thing that this order really enjoys. Indeed, if you start with a Mathon-balanced W is for weighing matrix of order 19, 9. It is balanced. It means, you have a weighing matrix, entries are 0, 1, minus 1. When you find the absolute value of all the entries, you're going to get actually a 0, 1 matrix. That 0, 1 matrix happened to be the incidence matrix of a symmetric design. And that symmetric design has those parameters, 19, 9, 4, right? And this was first constructed by Mathon and in 1983, appeared in a paper by Delany and Sarvate. But then later on, Mathon and Gibbons, did computer search and found, a number of balanced weighing matrices and showed that this is actually unique. There's only one of these. And ever since, this was called a sporadic balanced weighing matrix. It was a sporadic balance matrix. Just what happened really, quite luckily, we were able to not only this one, we could actually go from this unique one to an infinite number of balanced weighing matrix. And indeed, this is the class of the infinite class of balanced weighing matrices. Indeed, we were quite happy because, so far the literature will say, only classical ones really exist. And there are some sporadic ones. One of them was W1994. but we could actually sign, infinitely many of these. And this was just because of the nice structure that 1994 had. And I just don't want to go through the construction, but I have to say that we were quite lucky because, because of some luck, really. So I can't say more really in detail, right? Yeah, and the group that I use, for constructing that symmetric design was actually group Z2. But for this one, you had to go to a larger group. We couldn't really do it. The reason was that we wanted also, that to sign, some of the pluses we wanted to sign on the 1 to -1, and we wanted to make the rows orthogonal, so we had to go to a larger one, to a larger group. So for m equal to 1 here, again, for your entertainment, it's right there in front of you. It's 181, 81, 66. There's, of course, 0, 1, -1. You like to, well, of course, blues are 1, I think, 0 in white, 1 in blue, and -1 in red. So this is really interesting, that you have really one matrix which has so many nice properties. And that's why really I thought, that to bring to your attention this one. Okay. So I now want to talk about quasi-balanced weighing matrices. While we were doing that work, we noticed that many of these weighing matrices, they are not particularly balanced. Namely, when you really square off the entries, you don't get necessarily actually a symmetric design. You get actually something less than a symmetric design. Namely, either you get group divisible design, or you get a strongly regular graph, and so on. So we thought, that maybe, we introduced these, as quasi-balanced weighing matrices. So I'm going to talk about quasi-balanced weighing matrices now a little bit, and then I will present a couple of construction and indicate, an application. Okay, what is now quasi-balanced weighing matrix? So we have a weighing matrix. Enter is 0, 1, -1. Rows are all orthogonal. And the weight is k. So there is k non-zero in each row and in each column. And we denote it by WVK. And the rows are orthogonal. So the rows are orthogonal, as you can see. Here the rows are orthogonal. Yeah. Now, we call a weighing matrix balance if you square all the entries, you're going to get a symmetric balancing complete design, as I have really talked about before. In case the design is said to be signed, in case that you start with a weighing matrix, or you start with symmetric design, change one of the some of the ones to -1, and you get a weighing matrix, we say that that symmetric design is signed. These are, of course, the expressions, which is an old expressions introduced by Matan and before Matan too, right? So there was some interest in these objects, right? Now, a weighing matrix is said to be quasi-balanced when you square all the entries, you find the absolute value matrix, namely just to square all the entries of the matrix, and you find out that you actually get a matrix which has off diagonal, not precisely one entry, but two entries, maximum two entries, we said. So This, of course, includes also the balance weighing matrices, right? This concept includes balance weighing matrices. Now, a strongly regular graph with adjacency matrix A is signable. So, it was quite clear, that what we have to do, we have to really go to strongly regular graphs, because the strongly regular graphs, not all of them, some, actually all of them, when you multiply the adjacency matrix by its transpose, off diagonal, you're going to get 2 entries. And we say that a strongly regular graph with adjacency matrix A is signable if you change some of the ones to -1, you get a weighing matrix. You make the rows to be orthogonal to each other. Now, of course, there is a reason that we really wanted to do this, because if as soon as you have the rows orthogonal to each other, and you know that fixed number of 1 and -1 in each row, immediately you find Hamming distance. So you really can apply this to find nice codes. And indeed, we can find nice codes from these objects. You noticed yesterday they talk about cool, frost, and today freeze. Already we're in a stage of cool. Okay, so let me go a little bit into how really, what sort of classes we have signed. Number one is quasi-weight matrices are obtained from signing certain class of strongly regular graphs. It was quite really natural that we start, looking at strongly regular graphs and do an exhaustive search for small orders to see which one are signable. And then signing some divisible design graphs. And of course, we did with some computer search and signing some group divisible design. I'll go now through some of these. The first one is start with the prime power. Start with the prime power modulo -1, 4. So we have this. For any prime power -1 mod 4, there is a quasi-balanced weighing matrix of these orders, order 1 plus q 1 plus q square plus q cube, and of course the number of non-zeros q plus q square. And when you put the absolute value over all the entries, you're going to get a strongly regular graph with these parameters. Of course, here. Well, it seems like, sometimes this, maybe I don't know how to use, yeah. Anyways, this plays ground, yeah. Now, the other part is that you can decompose the complete graph over 1 plus q squared plus q cubed into 1 plus q Siamese sign strongly regular graph. Now, I'm going to show you what I mean by Siamese strongly regular graph. And with the above parameters, all of them share 1 plus q squared clicks of size 1 plus q. Let me just give you an example of this, okay? Here is 40, 12, 2, 4. So we expect actually if you apply all of this to q equal to 3, you're going to get, we're going to get 40 for the order, 1 plus 3 squared plus 3 to the power 3 is 40, and we're going to get the non-zero entries of 12 and get 2, 4. So let me show you the first one. No. Here we go. Before doing that, I have to really introduce a negocircular matrix. Now, a negocircular matrix is is a matrix. You can find all the entries from the row 1. So in here, you have this, you have, yeah, well, I mean, it's not working exactly. Here we go. So we have the first row 0, -1, 1. So you shift it to the right 1 unit and change the sign. This 1 becomes -1. And then the rest of the elements really follows. And the next row and the next row. So the first row is good enough to give you all the entries. And did I go too quick? Yeah, simple, like, yeah. And every negocirculant matrix is a polynomial in nego shift. This is what we call a nego shift. It's a nego shift. You can see that you shift to the right, you shift to the right, and then this -1 becomes minus in here. We can also have more general than this so-called omega circulant one. Okay. Now here I have a balanced generalized wave matrix 10, 9, 8. Let me explain what this one is. You have actually groups at 8, and then you have a matrix which has 9 non-zero in each row and each column. And you can see on the diagonal we get only 0 on the diagonal. And if you pick any 2 rows, multiply every element, skip the ones that has 0 in the column, then you get 8 left. You multiply every entry by the inverse of the entry below, and you put them all together, you get all the elements of the group. In this case is 8 over this order of Z8. You're going to get 1 time all the elements of the group. Now, the trick here is that we take now a BGW, a balanced generalized wave matrix, generated by nego shift of order 4. So if you get a nego shift, then the order of the group is 8. That really helps, with the fact that we want to have a weighing matrix. And indeed, we have to put also something on the diagonal, and we get now the first of the group of 4 of strongly regular graphs, order 40, 12, and so on. Keep in mind, that on the diagonal now I have, you see that negocirculant is on the diagonal. So the diagonal entries are all negocirculant of order 4. The rest is just, the nego shift being converted in order to make this matrix a symmetric matrix. So this is the first one, and then of course you have a second one. The advantage is that you can't check if something is wrong. You cannot check it. It's really large enough for you to be able to. It's the second one, and there's of course a third one, and there's of course a fourth one. So we get four of these. All of them share, that negocirculant that I put on the diagonal. So this is another way of decomposing, the complete graph. There's been some work on this sort of decomposition, by Klin and others. They have really sort of the idea of the Siamese is because they really share the same thing. The problem is that when you really move the shared part, the remaining is still interesting. You're going to get a distance regular graph actually, and that's why really there are interest in this sort of objects, and indeed, this is now, we have now introduced even something more to these graphs. Namely, we have put some minuses and pluses, and we know that the rows are orthogonal. We really don't know the consequence of this, really. We don't know how this can be really used in further problems. Okay. Here is the result of the complete research. We had 16946, and it just so happens that it is signable. We actually checked, all other ones with different mu and lambda for the strongly regular graph, but they weren't really signable. And the next one is that there is a link between these quasi-balanced weighing matrices and association scheme, and I only just mention that the association scheme obtained from these includes signed strongly regular graphs and also signed symmetric group divisible designs. So these are the two things that we have shown, are equivalent to certain association schemes. And I cannot go through that. So the paper is already out, and I am on the 50 days allowance that I can share with anyone. If you really like to see more of this, it's already on archive, and also you can just send me an email and I can share the paper with you. And just a couple of more minutes I have, let me just pose some open question. Number one is the sporadic Manton balance weighing matrix has led to infinite class of balanced symmetric design. So the question is, and I feel really it is true, the next one is there a balanced W 512512? We don't know the answer, but I just feel, my feeling is that, yeah, there is one. But indeed, I want to conjecture that there is actually a lot of those, but I don't think they're easy to be found. Namely, the order 2t squared plus 1, t squared and t squared minus 1 over 2. For every integer t, I think really there's one. Yeah. From our exhaustive search, it seems that only divisible design graphs are signable. Indeed, actually, it seems, all of the graphs that we have signed on, they can really, the absolute value can be made into a design. It can be made into a symmetric design. So I call it not a conjecture. Only divisible design graphs are signable. So not a conjecture, and that is it. And happy birthday, Doc, another time. And that is it.